Good afternoon, this is Schweitzer, and this is a quick little startup video. Um, just trying to answer some of the questions that kids are asking me about the Beers Law Lab and how it's going to work. Okay. So we have this little screw, and the screw kind of you'll see it, and it's a brass screw. So the amount of brass that's there is or the brass is there is composed of two things: zinc and copper. And there could be other things in there. I really don't know. Um, our goal is to figure out how much copper is in there. And we're going to do two ways, one gravimetrically and one spectrophotometry, I guess, Beer's law, using light spectrophotometry. Um, okay, so basically we're going to do our first step is we're going to take this um, and take this screw and we're going to place it in a beaker, small beaker. I'm going to say, 50 milliliters. The smaller the better because I want to try and cover this particular screw with nitric acid. The point of that is to essentially I could say dissolve the screw, which might be a good layman's term, but it's going to use a reaction that's called a redox reaction, and the actual reaction is it's located in your lab, man. You can see it. It's going to produce a couple things. It's going to produce Cu2 plus ions. It's going to produce nitrogen monoxide, and it's produce some water as well. We're more interested in this guy here, and these guys are blue. Okay. So we're going to take this guy, and it's not going to take real long, but we're going to take our little beaker, okay, and we're going to analyze that blueness of that solution. So we're going to do, first of all, it's in the fume hood. This is done in the fume hood. Okay, so make sure this this stuff right here is pretty nasty. Fume hood. It's brown. It's actually the main component of smog in big cities. Either way, so once it's all done, make sure the screw's all gone. Should be nice and blue. We're going to start adding some water to this. Now again, this is very concentrated. We're using concentrated nitric acid. So this could be just a little bit less than 14 molar, which is your typical nitric acid concentration. Some of it's gone because it went through the reaction, but not that much. So I'm going to eventually dilute this thing to 100 milliliters to give myself a standard size. So I'm in the fume hood, so I'm not carrying around this little beaker of really nasty nitric acid. Just add 50, 60, or some amount of water, distilled water, just so we're not too dangerous to move this thing around. Take it back to your station, and we're going to have a 100 milliliter gravimetric, I should say a volumetric flask. It looks something like this. Okay. All right. Now pour it in here, and you'll notice that even in this scenario, when you add the water, it got lighter and lighter and lighter blue. So what we're saying here is that the color of this thing, the blueness of this thing, is proportional to the concentration. Okay. And I think most people would agree that that is the case. Well, anyways, take some more water, maybe a beaker, fill it up to the neck, get yourself a squirt bottle, and just add up the water to the very end here. Okay. Get a cap, unless it's much more dilute at this point. Get a cap and mix it up back and forth, back and forth, back and forth. Okay. And at that point, we're going to test this thing. So at this point, we're going to grab a cuvette. Cuvette is probably, well, it's 1 centimeter by 1 centimeter by 1 centimeter. You'll see the little jars there. I usually keep them soaking in water. Just a handful of things you might want to know is that one side's got lines all over it. That's the side we touch. This side is the side that light goes through. Okay. Now you'll pull this thing out of the beaker that's got all sorts of these guys in here. They're all sort of in here soaking. Okay. Now what I typically do is I got this thing and it's gonna have some water in it. So what I'm gonna do is take my solution and I'm gonna fill it 3/4 of the way, halfway, switch it around and dump. And I'm going to repeat that process 2 or 3 times. You'll have water in the corners. We want to make sure that any water, and including the cap, that any water that's present, any liquid that's present, is the solution that's going to be in our um, that we want in there anyways. A small amount of water in this small little vessel can have an impact. All right, next, take it to the colorimeter. Make sure it's bone dry. I've seen people put these things in there wet. Do not. Drop. Now, the colorimeter, it's just a little device, and it's got a little box. You can lift it up, and you slide in yours. Now, there's typically right next to it, I'll have a blank. All right. And, it varies over the years, but there's a little calibrate button right here. You drop this in, make sure you're not touching there's little chem wipes. You can wipe these things off, but drop it in, and if you close it, your little computer box should read real close to 100% transmittance. Okay. And if it doesn't, then you can come get me. But otherwise, hitting that calibrate button will turn it to 100. Pull out your blank. The blank is just distilled water. And then drop yours in. And then read the value. So what this thing is telling you at this point is that, again, this machine is not super complicated, actually. This colorimeter machine essentially has a little LED light. Depending on the LED, okay, LED light, LED there, I guess, and it shines light through the area where the vessel is located, and it has just a little solar panel behind it. All right, and this goes back to the computer. All right, and the computer just reads a voltage, and it just says, okay, what's the voltage? And it just, the computer has no way of knowing what that voltage means. So all your do is when you hit blank, okay, this computer automatically sets up, okay, that whatever we have light going through is now 100% transmittance. That means that this thing is completely clear. And of course, it also knows that no light would be a 0 voltage, so that would be 0% T. Now, this machine does it automatically just by hitting that button. It sets a scale, okay? That completely clear, 100% T, no light coming through, 0 T, and it just says, okay, how much voltage. It knows, and on the computer side, if you get into it, you can actually see the voltage that the computer's getting. And of course, this would be 0 voltage. And it just sets up a linear scale between here. If this is I think before in the old machine, 0.41 volts was what this was. This is 0. Well, 0.1, 0.45, that's what I would typically get for a voltage on 100%. Okay, well, with that being said, if I have zero point 0.2, then my percent transmittance would be likely 50%. Okay, that's all the computer's doing. Okay, so when you see that um, kick out your number, so maybe you get, I don't know, 52%, let's say, percent transmittance. That means that on the scale, voltage-wise, you were somewhere in the middle. Okay. Um, all right. So when you look at this machine again, a couple things about Beer's law that you want to be aware of. Okay. And again, just a little background information again about this particular thing. Beer's law is really not a whole super complicated idea. We have here is essentially light is traveling through a container, and the actual Beer's law, you'll be using this version of it, but as the light travels through, there's a couple things that affect how much light can get through. Now, there's a thing called percent transmittance, which we've talked about, and we use that a lot. But there's another thing called transmittance. Good enough. And then there's another version called absorbance. Absorbance doesn't run on a 0 to 100 scale. It runs off a little bit different. Absorbance would be A, all right, or the absorbance. So as light goes through, there's a few factors that affect how much light gets absorbed. One is they call it A, B, C. A is the absorptivity constant. So it's a constant absorptivity. You'll see it in your book there. Constant that just how much inherently does this object absorb light? And it's a number. It's just a numeric. It's an equalizing variable to hook everything else together. B is your base path. Now, that means that the longer this path, the more light gets caught. So it's the length of the light needs to get through. This is 1 centimeter, which is equivalent to 0.01 meters. I'm almost positive they go to meters, but I have to verify if they leave it in centimeters, typically if they go to meters. And then C is just the concentration. Now, in concentration, obviously the more stuff you have in here, the darker it gets because less light gets through. So if you happen to have the absorbance, and you happen to have the base path, and you happen to have the concentration, then you can figure out the absorptivity constant. And you need 3 of the 4 variables. Okay. Now, again, we are going to do this. There's a question on your lab book that talks about this. We want to do this. But our main objective, our main method is not going to be using this formula, which is actually on your laminated sheet. It's been showing up once in the last 5 years, and before that, it never showed up. So, but it is there. Okay. As far as the AP exam is concerned. All right, so let's look at how we're going to solve this. Okay, we're going to do what's called a Beer's law plot, and a Beer's law plot is going to look something like this. Okay, and I'm just going to draw this out here. So in order, in order to determine a known, you must have an unknown. In order to determine unknown, you must have a known to compare it to. Known versus unknown. And essentially what we'll do through this process is prove Beer's law works. So what we're going to do is take a bunch of known samples, and we're going to say, okay, we know these samples, we know their concentrations, what are their percent T's? So on this side, I'm going to put concentration, all right, and we'll just put it right there, and then here, I'm going to put percent T. So every group is going to make a known solution. Now, as of right now, this could change, but as of right now, our known concentration is going to be 0.3 molar CuNO3. Okay. And again, if I only have one concentration, then I'm only going to get 1% T. So I want a bunch, in order to prove Beer's law, I want to have a bunch of concentrations. So I'm going to use this particular solution to generate a whole bunch of known solutions. So, for example, we have ourselves one of them several dilutions. Every team or every group's going to pick one dilution and make one known concentration. So 5 to 100 is a dilution, or 10 to 100 is a dilution. So how do we do this? How do we make this solution? So what I'm going to do is I'm going to take a pipette, all right, and be aware of how to use a pipette. If you don't know, ask. And I'm going to dispense 100 milliliters, 5 milliliters into a 100 milliliter volumetric flask. That's 5 milliliters. That's for this particular group. Add the rest of it up with water and mix it up. Now you'll notice that if one group makes a 5 to 100, the other group makes a 25 to 100, this one is going to be much bluer. Why? It's got more of the original concentrate. We're never going to get bluer than the original. All my dilutions get lighter blue, but the ones that are super light, like this one, you'll see it. All right, so I need, this is a 5 to 100 would be a form of a concentration, but I want the actual molarity. So I'm going to use M1V1 equals M2V2. And M1 is 0.3, V1 is, for this group, 5. That's every group's initial amount. And then the ending concentration is what I want to find. Ending volume is 100. And I'm just going to solve for this guy right here. So 0.3 times 5 is 1.5. Just going to put a calculator, 0.3 times 5. And then just divide by 100 to get 0.015. So the solution you just made is 0.0015 moles per liter. Okay, great. What's that mean for us? So every group is going to make their own concentration. So higher concentrations will be higher dilutions, and this one is the lowest concentration. Okay, it's this guy right here. Well, what's this guy's percent T? All right, go back to the your volumetric flask, take a sample out, and just like before with the cuvette, okay, pour some in, mix it up, pour it out. Pour some in, mix it up, pour it out. And then the third or fourth time, because we're going to use all this stuff anyways, take your sample and put it into the colorimeter. And close it up, make sure it's nice and dry, and you're going to get the percent T on the computer of that correlating concentration. So let's just say this group is 5 to 100, and it ends up being someplace like right here. Low concentration should have high percent T's. And then, of course, another group makes 10 to 100. So theirs is a little more concentrated. They'll have to calculate their own concentration out. They should be probably like right about here. And then the groups that get higher and higher dilutions or higher concentrations should end up having concentrations that follow along this line. All right. This just proved that Beer's law works. Now there's a video showing how to actually plug this into Excel, create a trend line, which the computer tries the best case scenario, and then the computer will generate what's called a y equals mx plus b equation. Now, why do I need that? Well, this is a very useful tool. It allows me to correlate any concentration to, even though I didn't actually test this particular dot, it's not my main dots, between dots, I can use the relationships. Okay, for this particular concentration, this is the percent T. Okay, well, how useful is that? Well, really, that's not super useful. But what is useful is for me to take an unknown substance, test it, and find the unknown substance's percent T. Now I can plug an unknown substance into that machine, it'll plug out its correlating percent T. and then I can cut across here and find out what that guy's correlating concentration is. Now that's a little bit messy on the graph. So rather than doing it manually, call it direct read, I'm just going to plug it into this formula. Plug it into x, the m and the b, which is the slope and the y-intercept, will be provided, and you solve out for the correlating y chord on the other side, chord on this side. So this brings us full circle to our unknown. You've already made your unknown. Have we made the unknown yet? Let's see what we did here. Okay, so yes, we did here. I showed you right here. Okay, so what we did was we took our brass screw. So let's just bring it all full circle. We took our brass screw, we dissolved it, we put some water in, brought up to 100 milliliters, and we tested it. Okay, so now we tested our unknown copper, and we came up with a percent T. So every group's going to have 2% T's that they're going to test, that they're going to have. They're going to have the percent T, okay, representing the concentration of the copper 2 plus ions in their screw. All right, and then they're going to have a percent T that's going to be just contributed to the group, okay, to one, prove Beer's law, and to create this tool, which is this guy right here, that allows us to relate any percent T to any concentration. So what we'll do, we'll take that value from this guy's percent T and plug it into our little tool. Now it's gonna take a little while. We gotta get all our data together for all my classes to get this relationship. So online, there will be an Excel folder that you'll want to download, and from there you can build your own graph and get your own y equals x plus b. Plug in your unknown value into that particular thing, and you'll find the correlating concentration. And of course, concentration is molarity equals moles per liter. And ours is 100, or 0.1 liters. Okay. From there, you'll know your concentration, solve your moles, convert to mass, and we're basically done. You can determine percent mass from that. So, just trying to answer some of the main questions. Follow your instructions in your lab manual, and answer all the questions in the lab book. Okay. Typically speaking, a lot of times in lab we do 3 trials, but just for this case, just do one screw, one trial. Okay. Thank you very much.